in binary frequency shift keying, for the transmission of two symbols 1 and 0, we use two different carriers with two different frequencies f1 and f2. We have studied that when these carriers have different phases, then the difference between these two carrier frequencies should be integer multiplication of 1 by Tb, and when the phases for these two carriers are the same, then the difference between the two carrier frequencies can be chosen to be integer multiple of 1 by 2 Tb, where Tb is the signaling interval for the symbol 1 or symbol 0. We have studied how to generate binary FSK signals and also studied the optimum receiver for the same. Now, we will calculate the probability of error for this optimum receiver and also evaluate the power spectral density of the transmitted BFSK signal. So, our binary FSK signal are S1 and S2 and they are orthogonal. Then we choose our two basis signals as phi 1 t equal to root of 2 by Tb cos 2 pi f1 t and phi 2 t as given here. Given this basis signal, for the signal set S1t and S2t, we can get the signal constellation as shown in the figure here. So, the decision boundary, presuming that both the symbols are equiprobable, would be the perpendicular bisector of the line joining the two signal vectors or signal points. So, this side it would be R1 and this side it would be R2. Given this, we can easily calculate the probability of error as follows. Probability of error is a Q function of the distance between the two signals divided by 2 and the standard deviation of the noise. So, distance here is equal to this distance. Remember, this is root e. So, this would be equal to root 2e divided by 2. Italic n by 2 is the power spectral density of the white noise. So, this is equal to now, in this case, for the equiprobable symbols, the bit energy is the same as the energy in the signal. So, we can write the probability of error in terms of the bit energy. Now, this expression is the same as we got for the binary amplitude shift keying. Now, let us evaluate the power spectral density for the binary FSK. We had studied the binary FSK transmitter, which is as shown in the figure out here. We have a binary data sequence, it passes through on off level. The output here are pulses with 2 voltage levels. For symbol 1 you get root E volts, and for symbol 0 you get 0 volts. So, that is indicated as empty. Out here it passes through an inverter. The output here is M bar T. Here for symbol 0 you will have root E, and for symbol 1 you will have 0. So, again pulses with 2 voltage levels, they get to the product modulators with phi 1t and phi 2t, and you get the outputs here. So, this is S1t. So, here for 1 you will be transmitting this signal waveform, for 0 we do not transmit anything, and in this branch, bottom branch, this is S2t. So, for symbol 0 we transmit this waveform, and for symbol 1 we do not transmit any waveform. So, the combination of this basically generates the binary FSK wave. Now, since the 2 oscillators which are used to represent symbol 1 and 0 are independent, we may view the resulting binary FSK wave as the sum of 2 binary ASK signals or 2 on off keying signals. One BASK signal operates with the oscillator of frequency F1, and the second BASK signal operates with the oscillator of frequency F2, and both are independent. So, let us try to calculate the power spectral density. Let us look at the top branch. In the top branch, consider this signal out here. This signal S1t could be considered as a signal which has been modulated by a random binary wave which takes value of root 2 e by Tb for symbol 1 and takes value 0 for symbol 0. Whereas, if you look in the bottom branch, you have this signal S2t. You could consider that this signal out here cos 2 pi f2t is being modulated by a random binary wave M2t, we could call it, which is root 2 e by Tb for symbol 0 and it is 0 for symbol 1. So, let us try to analyze the power spectral density for the top branch, and then we can extend that result to the bottom branch. So, in the top branch, let M1t denote random binary wave that modulates the carrier frequency F1. So, for symbol 1 we have the output as 8 times Pt, where Pt is a rectangular pulse which we can denote as shown here, and the value of A is equal to root of 2e by Tb, and for symbol 0 we have 0 multiplied by Pt. So, your m1t is of the form alpha k p t minus k t b minus some random variable beta. This is a pulse train for m1t, and alpha k is a random variable which can take the value equal to 0 or a has been given as root of 2e by Tb. Now, we know how to calculate the power spectral density for this type of a random wave. This is nothing but we had studied this form for unipolar line code. So, immediately we can write the power spectral density for this random wave m1t as follows. Now, if we choose our Pt to be rectangle pulse of duration Tb, then for this we know that Fourier transform is T sync Tbf, and considering this we can write the power spectral density for the m1t as the following expression. Because of the property of the sinc function, which is 0 at the multiples of 1 by Tb, all other terms in this summation series will vanish. Given this, now we can easily calculate the power spectral density of the binary ASK signal in the top branch as follows. We will indicate that as S of F1 is coming from the top branch related to the frequency F1, and we know that this is equal to 1/4 Sm Now, given this, we can calculate the power spectral density on the top branch. So, that would be by plugging in this expression into this. So, let us call this as S1f to simplify our notation. So, we can immediately get that, and that would be as shown here. So, this expression we just plug into this and we get this. So, having got the power spectral density for the top branch, similarly we can get the power spectral density for the bottom branch, and that we indicate as S2f, similar as what we got for the S1f, except that F1 has been replaced by F2, and now the total power spectral density of the output binary FSK wave would be the sum of this 2 power spectral density, because remember that 2 branches are independent, and if they are independent then power spectral density they sum up. And if you look at the plot for this power spectral density, this is what we get. Now remember that sinc x falls off as 1 by x for high value of frequency. So what this means, that this power spectral density will fall off as 1 by f squared for frequencies far off from f1 or f2. Now there is a form of binary FSK which is of interest in practical application, and that is spatial form of BFSK is known as Sunday's binary FSK. What is the property of this? It is as follows. We have 2 transmitted frequency f1 and f2, and they differ by an amount equal to the bit rate, and the arithmetic mean equals the nominal carrier frequency Fc For transmission, it is assumed that phase continuity is always maintained. I repeat please. For transmission, it is assumed that phase continuity is always maintained, including interbit switching times, and this is the definition for Sunday's BFSK, and we will try to evaluate the power spectral density for this special case of BFSK, that is Sunday's BFSK. So, let us evaluate that. Given this information for the choice of F1 and F2 and the average of F1 plus F2 is equal to Fc, we can express this spatial binary FSK signal as follows. Where, for example, minus sign could be used for the transmission of symbol 1 and plus sign could be used for transmission of symbol 0. And using a well known trigonometric identity, we can simplify this to the following expression. Sine of 2 pi Fc t, and this can be rewritten as cos is a even function. We assume now that symbols 1 and 0 are equiprobable and the symbols in the adjacent time slots are statistically independent. So, based on this we can make the following observations pertaining to the in-phase component and the quadrature components of the binary FSK signal, correct. So, remember this binary FSK signal has continuous phase. So, the first observation is pertaining to in-phase component is that this is completely independent of the input binary wave, correct. Irrespective of the binary wave, this is the in-phase component, and so for all time it is this quantity. So, the power spectral density of this is very easy to calculate. We indicate this power spectral density for the in-phase component as SIF, and this is the spectrum for the same. Let us look at the quadrature component. We see that the quadrature component is directly related to the input binary wave. During the signaling interval, plus minus will depend on which symbol we are transmitting, symbol 1 or symbol 0. But important to note that this form is nothing but a polar wave which can be generated by using the impulses of strength plus minus 1 passing through a filter HT whose impulse response is given here, correct. Given this now, we can easily calculate the power spectral density for this. This also we have done it earlier. So, the power spectral density for the quadrature component would be related by this expression. Right. The straightforward extension of what we have done earlier. So, to get your HF, again remember your HT is equal to this form. So, you integrate this quantity after multiplying by e raised to minus j2 pi ft, integrate over with time from 0 to Tb. That is how you will calculate the Fourier transform of this, and it is very simple to show that the Fourier transform turns out to be this, and from there the quadrature component's power spectral density is equal to this quantity, which if you plug in this expression for HF, you get equal to this. Okay. So, this is equal to squared, please. The squared of this is equal to this. Okay. Now, so the baseband power spectral density, which consists of the in-phase component and the quadrature component, can be obtained by addition of the two because both are independent. So, if I do that, I get the baseband representation for the Sunday's BFSK case, correct. And from here we can get the power spectral density for the modulated waveform, that is binary FSK, by using this relationship. So, this expression out here is plugged into this expression. What is more important to know that once I do this, I take this and put it here, this will contain two discrete frequency components, one at Fc plus 1 by 2 Tb, which I can call it F2, and other would be Fc minus 1 by 2 Tb, which I can call it F1. Now, it is important to know that these two discrete components help in synchronizing the receiver with the transmitter. And another important thing to observe is that if you look at the baseband power spectral density, then it falls off as the inverse fourth power of the frequency. So, whereas in the earlier case of BFSK, we had only sinc function squared. So, the fall off was at the rate of 1 by f squared. So, what this implies that Sunday's BFSK does not produce much interference outside the signal band of interest as an FSK signal with discontinuous phase at the interbit switching instance, correct. So, this is an important result, and this is because of the type of the shaping pulse which we have used. In ordinary binary FSK, the shaping pulse is a rectangular shape, whereas in the Sunday's BFSK case, we have a sine function as a shaping pulse. Now, quickly let us summarize the performance of the three modulation scheme which we have studied. So, we have studied binary amplitude shift keying, binary phase shift keying and binary frequency shift keying. So, as far as the performance probability of error is concerned, we find that performance of binary ASK and binary FSK, they are the same, whereas performance of binary PSK is better in the sense that binary ASK and binary FSK would require 3 dB more power than for the case of binary PSK for the same probability of error. But binary FSK will require much more bandwidth compared to binary ASK and binary PSK. Binary ASK and binary PSK both require same amount of bandwidth. The difference between the two spectrum is that there is a discrete component at Fc in the case of binary ASK case. Now, if we want to transmit the symbols at higher rate, this would necessitate that we reduce the signaling interval. But now, in all this study which we have done so far, it is clear that with the decrease in signaling interval, that is TB, the bandwidth requirement will also increase. So, the question is it possible for us to transmit at a higher rate without increasing the bandwidth? There are techniques available which are known as bandwidth efficient signaling or modulation schemes, and we will study this next. Thank you.